In today's class, we will try to first define line integral of a vector point function f r, where obviously this r is the radius vector, usual radius vector in three-dimensional a plane denoted as x I cap, y j cap and z k cap. I hope this is visible. So the line integral over a closed simple curve C, simple curve means which is continuous and which does not cross itself or overlap. So in that sense, a circle is a closed curve, a rectangle is a closed curve, a square is a closed curve. This type of curves are also closed curve, semicircle and all that. So simple curve, simple closed curve. Simple means which does not intersect or cross itself. Over it, if we evaluate f dot dr, we may represent it as from initial point A subject to a parametric value t, in terms of which parameter we can express this x, y, z. We may write f as f1 dx plus f2 dy plus f3 dz. Okay, where obviously this vector point function fr is assumed to have this type of structure, and so whenever we take this dot product, since r is this the radius vector, we have dr as dx I cap, dy j cap and dz k cap, and f dot dr takes the form this. And this integral over a closed contour does not depend on these endpoints. This is independent of the path chosen. It only depends on the initial point and the final point. And along with that I should add another word which states that if this f dot dr is 0, then you claim that this is, I think this is visible, I am writing it here also again, that if this f dot dr is 0, we say that capital F is a conservative field of force and we must have f equal to grad f for some scalar point function f x y z. Whenever we have circulation 0 or f dot dr is 0, we must have f expressible as grad f, and we all know that del cross f is 0, that means circulation is 0. So this is the initial word about line integral which we all should remember. And with this small introduction of what a line integral is, we move on to define the three basic theorems related with this vector integral. They are Stokes theorem, Green's theorem, and divergence theorem. This divergence theorem is actually known in the name of famous mathematician Gauss. So this is referred to as Gauss's divergence theorem. So these are the three basic theorems which we are going to discuss now. Number one is Stokes theorem, number two is Green's theorem, and these two theorems may be clubbed in a sense that they represent or expresses a surface integral or a double integral in terms of a line integral. While the third one, known in the name of Gauss's divergence theorem, actually relates a triple integral to a surface integral. So these two theorems relates a surface integral or reduces a surface integral from a surface integral to a line integral, these two, Stokes and Green's theorem. And the third theorem, divergence theorem, deals with a volume integral or triple integral and transforms it to a surface integral. With these initial talk, we move on to state what these three theorems actually stands for. And first let us describe Stokes theorem. First let us describe Stokes theorem. Stokes theorem states that if we have a closed contour C which encloses a surface S, we have a closed contour C which encloses a surface S. As for example, we may think of a very simple two examples. So this is a closed contour and it encloses this surface S, the upper surface of a cube. Similarly, if we have a circle, so this is the contour C, this is C and the surface is S. So this is a surface and this is a curve. And Stokes theorem states that if we have curl F dot in cap here in the left hand side, we can write F dot dr here. This is the line integral we just now defined. So this is a statement of the theorem. We are not concerned about the proof. This can easily be proved with a involved notion of multiple integral and a bit analysis. But here in this video, we are just stating this theorem and its utilities. So whenever we have a closed curve, I defined what we meant by closed curve, closed simple curve C, and it encloses a surface S. Here also we have a closed contour which encloses a surface S. There may be many examples. We may have this surface of a cylinder also. This contours closes the surface of cylinder. So for all this type of cases, if we have curl F here and this end cap, a word about this end cap. This end cap is the direction which is perpendicular to the surface, which is perpendicular to the enclosed surface. So end cap represents the perpendicular to the enclosed surface. Okay. So this is the statement of Stokes theorem, and where we have a closed contour which encloses a surface S, and curl F dot n cap ds is nothing but F dot dr. So we can change a double integral to a single integral. And in case of Green's theorem, just the opposite thing happens. There we represent a line integral. In case of Green's theorem, we have exactly the opposite. We have a line integral represented like this, m dx plus n dy, and this is equivalent to, if this is a simple closed curve C again enclosing a surface area S, we may replace this line integral by the surface integral del n del x minus del m del y into dx dy. So that is precisely the Green's theorem, may be taken as the opposite of Stokes theorem, because in this case we represent the equivalence of a line integral with a surface integral. So what about this type of vector point integrals, or vector integral theorems rather? They have actually originated from the requirements of mathematical physics, different engineering requirements and all that. Here just take a pensive look. This is actually a differential equation, and this differential equation is exact whenever we have del m del y equal to del n del x. We all know that partial derivative with respect to m and n. M and n are function of x and y both. M and n arbitrary function of x and y. Okay, x and y both. So whenever they are equal, this is exact, and whenever they are equal, or rather whenever this is exact, we have d of u something like this, and we have a closed contour, so this will obviously be 0, isn't it so? We have here d of u. This is a total derivative whenever this equation is exact equation, and we have del m del y equal to del n del x. We all know that in case of exact equation. So this will be 0. So in many cases we have this type of line integrals which may turn out to be difficult to calculate, but if we convert it to surface integral, it becomes easier. This may be a constant, this may turn out to be a constant, and we can take it out of the integral sign and then we get the surface area only. In any case, we have stated Stokes theorem and Green's theorem. Both of them are, this is Green's theorem, and you should remember that Stokes theorem is actually curl f dot n cap ds is equal to or same as f dot dr. So we can compare them. This is curl f dot n cap ds, where n cap represents the this n cap is perpendicular on the surface which is enclosed by the curve C. Now we move on to state the other one known as Gauss's divergence theorem. The Gauss's divergence theorem actually converts Gauss's divergence theorem. This converts a triple integral or a volume integral to a surface integral. Let us write it like this. If we have a volume V which is enclosed in a surface S, this surface encloses this volume. In case of the other two theorems, Green's theorem and Stokes theorem, we have a simple closed curve C which encloses a surface S, and here we have a surface S which encloses a volume V. We can easily think of a sphere where we have three great circles and we have three contours. These three great circles may be taken to be three contours. We all know that one is the XOY plane which cuts the sphere. In this circle C2 we have XOZ plane which cuts the sphere in C3, and we have this one as YOZ plane which cuts the sphere in C1. So we have three different great circles of this sphere, isn't it so? This is the radius of the sphere which is cut by XOY plane, and this one is XOZ plane, and this one is YOZ plane. We have 3 radius, equal radius. We all know this. So this encloses the surfaces of 3 great circles, and all these 3 contours or all these 3 surfaces actually encloses the volume of the sphere, isn't it so? So this concept or notation, we may write Gauss's divergence theorem as divergence f dv is equal to nothing but f dot n cap ds, and obviously this n cap is perpendicular to the surface S. This we must remember. N cap denotes the perpendicular direction, unit vector perpendicular to the surface S, which is enclosed, which encloses rather the volume V. So we have stated the 3 very important theorems related to vector integral form: Stokes theorem, Green's theorem, and divergence theorem. Okay, in case of Stokes theorem and Green's theorem, we should remember that we convert surface integral to line integral. Okay, this is Stokes theorem, and in case of Green's theorem, we have actually the reverse of it, where we express a differential form mdx plus ndy in terms of the surface integral, which is del n del x minus del m del y into ds. Actually ds represents dx dy, the 2-dimensional plane. And in case of divergence theorem, this is Stokes theorem and this is Green's theorem. But in case of divergence theorem, we have a triple integral over a volume V, and we have here divergence of f or del dot f. We should remember this is del dot f. We may write it dx dy dz. Then it turns out to be f dot n ds. F dot n ds. I am not writing it dx dy or dy dz or dx dz. Anything can happen. This is for your clarification. I hope these 3 are visible clearly. So have a look at these 3 theorems, and we move on to give an example of this divergence theorem. Let us verify Gauss's divergence theorem for the vector point function f, which is written as xi cap minus y square j cap plus z square k cap, where the volume taken over the volume enclosed within the surface x square plus y square equal to 4 and z equal to 0 to z equal to k. Let's say z equal to 3. So this is a specific example of Gauss's divergence theorem. So what Gauss's divergence theorem states? It states that V of divergence f dv, or we may say write it as dx dy dz, since the function is of x y z only. So we may write it as this. So first we should find what is del dot f or divergence f. If we see, look at it, this f, so it turns out to be 1 minus 2y plus 2z. Simple. So we may write it as 1 minus 2y plus 2z dx dy dz. So to verify divergence theorem, we should show that this volume integral is same as the surface integral. According to the Gauss's divergence theorem, this volume integral is same as the surface integral of f dot n cap ds, where ds is the surface of this cylinder. This is nothing but a cylindrical surface. If we draw a picture of it, it looks like this. This is z equal to 0 and this is z equal to 3. And the circles x square plus y square equal to 4 is the cylinder. So we should be able to show that this volume integral is nothing but equal to this surface integral.